design and the ductile detailing of the bridges. And to present the lecture, we have with us Engineer S.K. Patel sir and G.H. Patel sir with us. I personally feel very privileged to give introduction about S.K. Patel sir, because my father also works in the as a deputy executive engineer in the same department where S.K. Patel sir works as the chief engineer. And when my father came to know that I'd be introducing sir today, he remarked that sir is the most reputed and most respected person of the R&B department of Gujarat. So as I already mentioned, S.K. Patel sir is currently the Chief Engineer and Director of the Staff Training College of the Roads and Buildings Department. Sir completed his bachelor's in civil engineering from the Regional College Surat and completed his post-graduation in the Master of Business Administration. After graduation, sir was employed oil sector giant ONGC in the year 1988 and worked there for 12 years. During his tenure in ONGC, sir was mainly associated with offshore projects of Bombay High region and has undergone specialized training on structural dynamics with DNV Oslo, Norway in the year 1990 and deep water offshore structures under Medintech, Norway in the year 2000. Since 2001, Sir has been employed with the Roads and Buildings Department, looking after the training and development of the officers of the Roads and Buildings Department and the design of the bridge projects of the Gujarat government. Sir is also involved in the benchmark projects of Gujarat government, such as the Mahatma Mandir, Cable State Bridges, Statue of Unity, etc. Sir has published more than 15 papers related to offshore structures, bridges, etc. And Sir has worked as a member of various committees formed by the state of Gujarat from time to time, like the High-Rise Building Committee for all the municipal corporations and authorities. Introducing J.H. Patel sir. So J.H. Patel sir is currently the executive engineer in the design circle of the Roads and Buildings Department at Gandhinagar. And sir has over 36 years of experience in bridge designing, and sir has designed the bridges like the Cable Stayed Bridge, flyovers and river bridges also. Sir's major projects involve the signature bridge at Dwarka, which is single-stayed bridge with the largest single span in India. And Sir has also on the 6-laning work of SD Highway and the Ahmedabad Rajkot Highway, and the Narmada River Bridge, which is near the Golden Bridge, which is near the Golden Bridge. So without taking much of time, I would now like to hand it over to S.K. Patel, sir. Thank you.
Thank you, Misa, for a nice introduction. Thank you, Professor Sanghvi, for giving us opportunity and to share our experiences in the bridge design to the participants of the various area. The whole lecture, it is divided into 2 parts. The first part I'll take, and the second part will be taken by my colleague, Mr. J.H. Patel. Coming to the seismic design of the bridges, before that, I'd like to highlight the contents of my presentation. Briefly, I will tell about the Road and Building Department, and then the bridge inventory of the R&B department, bridge structural form, components, materials, then the seismic design provisions as per IRC, prevailing IRC, and challenging for the bridge engineer. In nutshell, the Road and Building Department, it is a department of Government of Gujarat, who is looking after planning, designing, construction and maintenance of roads, bridges and building of Government of Gujarat. We have different types of road like National Highway, State Highway, MDR, ODR, VR. Altogether, it is more than 1,16,000 kilometers. And we have different kind of bridges like major bridge, minor bridge, culvert, city works. So it is a large inventory. Currently, we have the 140 ROB works which are going at planning and execution level. This is the first time in history that such a large quantum of work of ROB due to the DFCC project, as well as the government of Gujarat has taken up the Fatak-less Gujarat. That is, there is no level crossing in the entire Gujarat within coming, say, 5 years. Then we have some benchmarking project like Cable Stayed Bridge at Bet Dwarka, which is a single span largest bridge in India, which is having a 900 meter total length, main span 500 meter, and pylons are curved pylon. This is the first time, I think, in the world, hardly you will see such type of curved pylon. It has four-lane carriageway with footpath, and footpath will be having a solar panel. Then we take up building work also, residential as well as non-residential. The broad function of R&B circle, that is, it is our in-house design wing. We look after the designing of bridges, buildings. Then we also carry out proof checking for the flyover ROB of the urban development department. In last almost 5 years, the government has issued notification that all the designs will be proof checked by UDD departments, will be proof checked by R&B department. Then we provide technical support to the field office of R&B divisions. Now in the detailed design of the bridges, we follow IRC standards. Now, if we see in the later part that in the bridge in year 2011, IRC 112 has been published by IRC, and that is limited design. Earlier then it was a working stress design. Then we use the latest software like Midas Civil, RM Bridge, Adapt, all these are international software. Then we consider load combinations for ultimate limited and service limited condition. Then construction conditions are conditions. These are the broad design considerations. Coming to the inventory part of the R&B department, we see here that almost 25% bridges are more than 50 years old. This is very highly challenging, because this bridge, either we have to go for the retrofitting, strengthening, restoration, or we have to go for the reconstruction. Now government has introduced a budget item for the addressing this aged structure, so that in the recent budget we are taking up this issue. Coming to the type of substructure, we know that in this section, the masonry, unenforced masonry, that is very vulnerable. So in the total inventory of the major and minor bridges, almost again 25% substructures are vulnerable to the seismic loading. So these also need a retrofitting of the structures. Now coming to the general bridge structural form, we have different kind of structural form like beam, truss, arch, suspension, balance cantilever, and then cable stayed. So all these structures are widely used. The beam is like a conventional transferring the load as a beam action. Then there is a truss section, mostly steel structures. Then arch beam, maybe concrete arch, steel arch. Then we have a large span structure like cable stayed, suspension bridge. Then this is a balance cantilever. Now this balance cantilever, this photo is of this is a bridge on Narmada. It is Chandar-Poicha road. Now the problem with this structure, the balance cantilever, it is the large reflection of the cantilever tip. 48, the same issue we are facing, and nowadays if you have seen in the newspaper that today also there is a traffic jam of almost 2 kilometers. So this bridge structure is okay, but the issue is a deflection. Now coming to the selection part of the bridge structural form, there are various parameters like design discharge, gauge length, whether the river is perennial river or only seasonal river, availability of local material, soil type, navigational activities, because now the government has declared waterways in so many perennial rivers. So that navigation required, there are different categories of waterways. So that also we have to consider. Then traffic demand, because if we see that all these 4-lane roads are converting into 6-lane and 6-lane to 8-lane. So this traffic demand is going exponentially high. And of course, availability of fund and priority of the fund. Now coming to the bridge material, mainly if you see the old bridge, there we use stone masonry, brick masonry. And then with the invention of concrete, almost in the recent, say last 30, 40 years, all the bridges are concrete bridges. Either is a plain concrete, is a mass concrete, or is a reinforced concrete. Then superstructure PSC, pistos concrete also. Then steel structures, then composite material, a composite of steel concrete, steel deck and steel girder and RCC deck. Then earlier bridge, that is in the timber. Now broadly, the components are superstructure, bearings, substructure, foundation, and there are a couple of miscellaneous items like expansion joint, parapet, bearing cord, detent wall, etc. Looking to the graphics, if we see here the superstructure, the mostly not like building in the seismic aspect, in the bridge structure, the superstructures are resting on the bearing. So it is simply supported. In few cases, you will see like in the balance cantilever, it is integral at the pier. Otherwise, mostly because if you go for the integral structure, it is better in the seismic performance, but the cost will go very high because of the differential settlement issue. So that is why most of our bridge inventory, rather I would say that more than 99%, it is of the simply supported kind of structure. So the load transport to the bearings, then it goes to pier cap, pier, and then pile cap and pile, or maybe open foundation, or maybe well. Then there is a well cap and well. Now, in the bridge structure, if you see, there are a lot of combinations. The superstructure type, there are a number of types, like from solid slab, voided PSC, voided slab, T-beam slab, PSC, T-beam slab, box, that is RCC box, PSC box. So all the superstructure combinations, as well as you have a combination in the substructure also and foundation also. So all these selections, that depends upon your, again, the type of soil, the design discharge, nature of gorge, whether it is a deep gorge, it's a shallow gorge. So that the initial in the general arrangement of the bridge, that we decide based on the performance aspect and the economy aspect and the maintenance aspect. The recent one, that is if you see spine and rib construction, later I will show you the actual picture and the details. And the steel truss and boasting, mostly in the ROB, say up to 40 meter we go for the girder type of structure. Otherwise, it will be the steel truss or boasting truss type structure. So these are some examples. These are PSC, RCC box. Then you have this is a box type thing. This is a girder type thing. Again, if you see, like in Ahmedabad right now, the 6-laning work is going on, where mostly you will see the PSC girder type of situation, because it will facilitate, because once a foundation work is going on, at the same time you can construction of the girder also parallelly can go in the casting yard. So you can save the time. And not only that, but you can save a lot of time also. Similarly, steel girder, but steel girders are comparatively costlier as compared to PSC or RCC girder. This is the spine and rib type superstructure. Now, this is a recent development in the bridge construction industry, where it is a segmental construction, where the spine it is casted separately, and the segments are casted with this separate launching girder, and then you have a rib again installed with the lighter gantry girder. So this structure, it is specially for the 6-lane bridges, very popular, and nowadays in the couple of projects, like in Gujarat also, the cable stayed bridge at Bet Dwarka, we have adopted this type of structure in the other than cable stayed portion. In cable stayed portion, it is a steel structure. In the ROB again, it's a boasting type. Then you have steel girders, RCC girders. ROB is a very simple structure. Mostly it's a earth retaining structure. It's a box type structure. Now coming to the bearing part, mostly if you see these smaller bridges, minor bridges, then there is no bearing. Like solid slab less than 12 meter span, there is only tar paper bearing placed above the top of the pier or abutment. But majority of the bearings are elastomeric bearing, pot PTFE bearing, and roller rocker bearing. Coming to the seismic part, the roller rocker bearing is a rigid type of thing, and nowadays we are not using this, but mostly we use pot PTFE bearing and then elastomeric bearing with the seismic restrainer. And pot of PTFE bearing, there are 4 combinations, like is a fixed bearing, then you have a LG, longitudinal guided, transverse guided, and then free bearing. And sometimes we use pin also to transfer lateral load. Coming to the substructure type, mostly as we saw that almost 25% substructure are masonry, pier and abutment, which are very vulnerable. Then we have mass concrete pier and abutment. Suppose pier height is less and the bridge category of the say ODR, MDR road. Then for the economy aspect, we go for the mass concrete. It is only taking stability from its own weight. And there is only temperature steel, skin enforcement. Then we have RCC pier and abutment. RCC pier and abutment that we design for the seismic force, and then all this ductility requirement that we check. Then there are steel frames also. Now coming to the foundation part, we have, depending upon the soil type and load, we have step footing. Then we have, like in mass concrete, we simply provide steps. In the RCC pier, we provide an isolated foundation. Then in the some coastal area where SBC is very less, we go for the rough foundation also. Pile foundation, nowadays it is widely used, especially in the urban flyovers, because the excavation of such a deep for the open foundation, there is a large area, then there are a lot of utilities, so many issues. So pile foundation is very much popular and convenient also. Well foundation, it is day by day it is getting obsolete. In the recent past, I would say that in the last 10 years, hardly 2-3 projects we have used the well foundation, especially in the bouldery strata, pile foundation feasibility is very less. Coming to the substructure part, especially for the ROBs, you see there are different types of pier shapes. It may be circular, it may be portal type thing, maybe wall type, and different geometrical configurations. So each shape has a different seismic performance. So there are different, it's a frame type thing, there is a large portal. Now coming to the bridge design philosophy in general. So we see the constructability, serviceability, safety, aesthetic and economy. Especially in the bridges, the flyover ROBs, the aesthetic, it is very important because it should not give monotony. This is the flow chart. First we define the purpose, then we go for the functions, then parallelly we have to see the material availability, then selection of form, then style, then it is a final product. Now largely we follow the IRC, but some cases like the cable stayed bridge where IRC provisions are not adequate. In that case, we follow ASTO code as well as Euro code. Especially for the wind load part, there were IRC provisions are not adequate, and IRC stipulates that the rigorous analysis to be carried out as well as the other literature is to be followed. The IRC 6, it is a standard specification and code of practice for road bridges. It gives you all loads. Then there is a IRC 112, that is code of practice for concrete road bridges, where it is limited. It started in 2011. Actual start maybe in 2015. Then recently we have guideline for seismic design of road bridges. This is a very exhaustive guideline and it is published in May 2018. So where even the examples are given for the calculations of these all bridge examples. Coming to the seismic design philosophy of bridges, under design basis earthquake, a moderate earthquake which may occur more frequently in the life of structure, the bridge should be able to withstand earthquake with minor structural damage. It is similar to building. Under the maximum considered earthquake, a large earthquake which may occur once in life of the structure, the bridge may be subjected to significant structural damage but not collapse. So basically this is a collapse prevention stage. The damage should be readily accessible for inspection and repair. Like the hinge formation in the pier and the foundation, the hinge formation we should detail or we should capacity design should be such that the hinge formation should occur only in the pier portion. The bridge with the design life up to 100 years may be designed for design-based earthquake only. The bridges with the design life more than 100 years may be designed for both design-based earthquake as well as maximum considered earthquake. Now these are the various seismic design provisions are given in the IRC 6. The applicability, all the bridges except culvert and minor bridges up to 10 meter span in all seismic zone and bridges in seismic zone 2 and 3 satisfying both limit, that is total length not exceeding 60 meter and span not exceeding 15 meter. So it means the small bridges less than 10 meter span, there is no need for seismic design. And for the bridges length more than 60 meter, that is a major bridge, where the span more than 15 meter, in zone 2 and 3 we did not say, but in the zone 4 and 5 we have to design. Coming to masonry and plain concrete arch bridges with span more than 10 meter shall be avoided in zone 4, 5 and near field region. So near field region, that is near the fault line. Two horizontal components are taken as of equal magnitude and vertical component is taken 2/3 of the horizontal component. The zone 4 and 5 effect of vertical component shall be considered for all the element of the bridges. Effect of vertical component may be omitted for all the elements in zone 2 and 3 except pre-stressed concrete deck, bearing and linkages, horizontal cantilever structural element for stability checks and bridges located in near field region. Apart from that, a special investigation such as site-specific spectra, independency of component motion, soil structure interaction, structural nonlinear effect required for bridge more than 150 meter span, bridge with pier taller than 30 meter in zone 4 and 5, cable supported bridge such as cable stayed bridge, extra dual bridge, suspension bridge, arch bridge having more than 50 meter span, bridges with seismic isolator, damper, etc., and bridges using innovative structural arrangement and material, and bridges in near field region, that is 10 km from the known active faults on both sides. The computation of seismic response for most of the bridge, elastic acceleration method is adequate. In this method, the first fundamental mode of vibration is calculated and corresponding acceleration is read as per the response vector given in the code. The elastic response vector method is adopted for more complex structural systems such as continuous bridge, bridge with a large difference in pier height, bridge with which are covered in plan. And then we combine the component motion, that is the force in the x direction, y direction and z direction. So if we take x direction full, then 30% from the y direction, 30% from the z direction. Similarly, in the y direction and z direction. The horizontal seismic forces, the specific force to be registered FEQ is equal to H into dead load plus appropriate live load. And then the EH, that is horizontal specific coefficient, that is Z by 2 into importance factor into SA by G. Now the live load, we take the fraction of live load. Live load we take only in the transverse direction, that is 20% of live load. Now for the computation of the fundamental period of the bridge, any rational method can be adopted. The IRC 112 is the guideline. IRC SP 114 gives you how to compute the fundamental time period. 5% damping is considered. Here, not like in building, here the 5% it is for concrete as well as steel, both. The fundamental period, that is given by 2 into square root of D divided by 1000 F, where D is appropriate dead load of the superstructure and live load in kilonewton. And F is a horizontal force in kilonewton required to be applied at the center of mass of superstructure for 1 mm horizontal deflection at top of the pier and abutment for the earthquake in transverse direction, and the force to be applied at the top of bearing for earthquake in the longitude direction. Again, coming to the importance factor, it varies from 1 to 1.5. For normal bridges, all bridges except those mentioned in the other classes, importance factor is 1. For river bridges and flyover inside cities, bridges on national highway, state highway, near port and economic center, or crossing railway line, it is 1.2. Now for the large critical bridges in all seismic zone, long bridges more than 1 kilometer across perennial river and creek, bridges for which alternate route are not available, in all those cases, importance factor is considered as 1.5. Now the live load component, the seismic force due to live load shall not be considered when acting in the direction of traffic, but shall be considered perpendicular to traffic. The horizontal seismic force in direction perpendicular to the traffic shall be calculated using 20% of live load, excluding impact factor. Now, as we know that the earthquake, that is extreme event, and the water current, that is the design discharge, that is also extreme. So this cover depth is calculated based on the extreme flood event. So scour depth under seismic condition is taken as only 0.9 times the maximum depth of scour. Similarly, the HFL, the flood level of calculating hydrodynamic forces and water current force, is to be taken as average yearly maximum design flood considering 7 years data. Also, the hydrodynamic and earth pressure forces under the seismic conditions. Hydrodynamic forces act on submerged part of the structure are to be transmitted to the foundation. Additional earth pressure due to earthquake act on retaining portion of the abutment shall be considered as per IS 1893. These forces shall be considered in the design of bridges in earthquake zone 4 and 5. Now the response reduction factor, especially in our kind of structure where it is simply supported, superstructure simply supported, the response reduction factor for the pier abutment as well as for foundation, the values are given in the IRC. There are two values given with the ductility and there is without ductility. The different components, the values are given. The liquefaction in case of loose sand and poorly graded sand with a little or no fines, there will be high potential of liquefaction. Founding bridge on such strata should be avoided as far as possible. Alternatively, foundation shall be taken deeper below liquefiable layer. Now the IRC SP 114, it gives you the evaluation of liquefaction potential, the separate appendix is given for calculations of the liquefaction potential. Coming to the foundation design, for design of foundation, the seismic force after taking into account the response acceleration factor R, it may be taken 1.35 times and 1.25 times the forces transmitted to it by concrete and steel structure respectively. So for concrete structure it is 1.35 times and for steel it is 1.25 times, so as to provide sufficient margin to cover possible hinge forces, higher forces transmitted by substructure arising out of overstrength. Ductile detailing part, mostly it will be covered by Mr. Er.J. Patel, but mainly in the IRC 6 provisions, it gives mandatory provisions to improve the seismic performance of the bridges. The bridge located in seismic zone 3, 4 and 5 may be specifically detailed for ductility as per provision of IRC 112. So in IRC 112 there is a separate chapter given for ductile detailing. In zone 4 and 5, to prevent dislodgement of the superstructure, reaction blocks shall be provided. Pier and abutment cap shall be generously dimensioned to prevent dislodgement of the superstructure under severe ground sacking. So there is a minimum width, the sheet length is given in the IRC depending upon span, depending on height of the pier. And there are some provisions of a recommendation type of nature, like special devices such as shock transmission unit, base isolation, use of lead rubber bearing, dampers, seismic fuse, etc. may be provided to improve the seismic performance of the bridge. Continuous superstructure, all integral bridge may be adopted, but as I mentioned earlier, that integral structure, it becomes costlier compared to this simply supported structure. Where elastomeric bearings are used, a separate system of arrestor control in both direction may be introduced to cater a seismic force on bearing. Now this IRC 114, SP 114, it gives you the guideline on the various aspects. So it is nicely narrated about the conceptual design part. So it has given the preferred structural configuration of superstructure, substructure, bearing, expansion joint, seismic devices and foundation design. That which type of superstructure is preferred and which is not preferred as per seismically not preferred. Then it will also give you the general design provisions like strength, energy dissipation, capacity design, overstrength factor, then ductility, capacity and demand, seismic design method, ductile detailing. It gives you elaborately in the various chapters. Now there are few challenges which is faced by the bridge engineer. We know that for any infrastructure we need a land. So like if you see the DFCC project or maybe the bullet train project or Mumbai Vadodara Expressway, we see that the availability of ROW, right of way, it is very restricting because these 140 ROB work which is going on, we are facing a lot of difficulties. And in view of this, there is a lot of revision in the design. So we prepare the general arrangement considering that the ROW will be available as per the requirement. But in the reality, if we see that during execution of work, there is a lot of opposition from the local user, local habitats, and then we'll end up with the revision in the structure. Then the availability of casting yard and a distance from construction site. Because right now we have almost 3-4 projects which are more than 3 km long. So there are huge number of girders. So where to cast, how to transport, again the span arrangement, the trailer which are carrying the girder, the availability of the road, a lot of issues are there. So those things we have to face a lot of challenge. Then the presence of utilities. Like in Ahmedabad, we have a lot of flyover works are going on. We could see even utilities 10 meters below ground level. So during piling work, because we don't have the utility mapping right now. So to the extent possible, the ground penetrating radar, GPR and those techniques are available. But still the smaller dia utilities, it is very difficult to locate. So those utility, in many cases, it resulted in the revision of foundation and the relocation of pier, or maybe the single pier we have to design as a portal like that. Then there are excavation issues. We see in the newspaper that the deep excavation, especially in building also, the double basement, triple basement. Now in the high-rise building in Ahmedabad, there are proposal of the 5 basements. So the excavation issues, it is highly challenging, adjoining property, safety of our structure. Then traffic management. You see in the SG highway, we are facing a lot of problem with the diversion of traffic. Then constraint on construction activities during daytime. Now coming to the seismic retrofitting part, we have seen that in the Gujarat we have large inventory of masonry bridges. So those bridges required seismic retrofitting, and mostly we go for the masonry type structure. We go for the jacketing of pier and abutment, and it will give some confinement and it can work. So the as I mentioned earlier, the new budget item, we are going with the detailed investigation of those bridges, whether it will qualify for the retrofitting, or if the expenditure is more, we may go for the reconstruction of the entire bridge. Again, the aging, because in Gujarat, see both things, we have the longest sea coast. The specially structure located in the coastal area are very vulnerable to the adverse climate and very severe condition. Then availability of fund, of course, the fund availability and fund priority decided by the government, but this is a major factor. Then non-availability of nearby alternate routes, especially during the retrofitting work. We need to divert the traffic, or we have to give alternate routes. Sometimes we have to close the traffic. So that also affect the non-availability of nearby route, also affect the retrofitting and reconstruction activities. So with this, I'll conclude my session, and Mr. Er.J. Patel will take about the design aspect in detail. Participant who have any doubt or any query, because this is a very brief lecture. So this is my email address, skpatel23@yahoo.com. It is 23, not 123, so that one should not commit a mistake. So with this, I end my lecture. Thank you all. Sanghvi sir.
Sir, good afternoon.
Yeah.
Sir, is there any depth criteria for the foundation for the piers?
Depth criteria. Yeah. Say there are again foundation type. You have open foundation, pile foundation, well foundation broadly.
For open foundation, sir?
Say like pile foundation. So definitely one has to see the state of the soil. How much friction is available, whether it's a friction pile or end bearing pile. Coming to the open foundation, we have this cover depth. So like if the bridge is located in the sandy layer, so then sand we have to carry out the soil investigation. Then you work out the potential, this cover depth that is given in the IRC, and accordingly the foundation depth, the even open foundation should be deeper than the cover depth. So that is a depth criteria. Is it okay?
In case of road bridges,
Yeah.
in
Now,
case
in
of
case of road bridges, there is no depth criteria, but that criteria is there because, like in the Rankine theory, if you see the minimum depth of foundation. So for availability of SBC, you need to go that much deeper, but there is no phenomenon of scour.
Thank you, sir.
Okay. Any question? So I think Mr. J.H. Patel can start.
Yes. Sir, are you getting my PPT?
Hello.
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 Yes, sir. No, we can't see your presentation, sir. Your screen is visible.
Now it's visible?
No, sir. Share again. Yes, sir. Now it's visible.
Right.
Yes, sir.
So can I start now, sir?
Yes, sir.
Thank you very much. Now I will talk about the ductile detailing in the bridges. As SK Patel sir has explained everything about the basic fundamentals, basic structures, and how basic form of the bridges. Now our code IRC 112, that is for the design of the structure. IRC 6 for 2017, that is for the loading of the bridges. It includes the seismic load also, how to calculate the seismic load. IRC SP 16, that is special publications 114 2018, is for the particularly for the design guideline for the seismic design of bridges. These three codes provide us the guideline for analyzing and seismic action acting on the bridge. Also, it provides the understanding of various methods for seismic analysis, loading criteria, and design procedure for every structural member. It also gives guidance for detailing of the reinforcement for every member. It includes the ductile detailing. Also, it gives the idea about seismic isolation and its method. Now, first of all, ductility. Now, what is ductility? As per Indian Road Congress, IRC defines the ductility as a ductility of structure or its member. It is the capacity to undergo large inelastic deformation without significant loss of strength or a stiffness. Thus, the ductility is a property of member to absorb heavy force with help of having large deformation which may be inelastic in nature without collapsing or failure of that member. So ductility is very much important. As in the case of seismic event, we undergo very large deformation, a very large force is generated on the structure. So ductility is very, very important for the any ductile structure seismic design of the structure. Now you can see this is the basic graph. The first portion dy is our this yield strength, this elastic limit, and the ductility is defined by du over dy. That is altimeter deformation. Now, what is the advantage of ductility? The advantageous properties availed by the suitable reinforcement detailing, which is suggested by the course. The preferred choice of location and amount of reinforcement in reinforced concrete structure to provide for adequate ductility in them is called the ductile detailing. So, it by providing necessary reinforcement for ductile detailing, we can define the certain portion where there is a potential of hinge formation, so we can avoid that formation over there. In steel structure, it is a design of members and their connection to make them adequate ductile. The lack of ductile reinforcement can cause a serious damage to the structure. In some cases, it may lead to failure of whole structure or a functionality of a structure. Now, in case of seismic condition, we have to mitigate all the other disasters. So in that case, our road should be not damaged, or our connectivity may be may not be disturbed because of the failure of this type of bridges. If the river bridge fail, then what happens? We cannot cross the river. So our whole this rescue work will be affected. So the ductility is very, very important for bridge to avoid this type of failure. Thus, the ductility may be ensured by required reinforcement as specified by the code provisions. Now you can see the lack of ductility provision. There are a number of failures in the structures. Like here we can see the failure of the bridges. This is also a one type of failure in the ductility. Here also a provision ductility, as in the portal, the hinge formation may be at the top and at the bottom of the pier. Here also we can see the failure. This is also a failure because of the poor ductility provision. Here also there is a problem with not 100% for the ductility, but the lack of confinement over there. Now come to the design philosophy. Under design basis earthquake, a moderate earthquake which may occur more frequently in the life of a structure, the bridge should be able to withstand earthquake with minor structural damage. So we can repair it easily. Under maximum considered earthquake, a large earthquake which may occur once in a life of structure, the bridge may be subjected to significant structural damage but not collapse. The damage should be readily accessible for inspection and repair. The bridge with the design span of up to 100 years may be designed for DBE only. The bridge which design life is more than 100 years may be designed for both DBE and the MC, as it was explained by the Sir S.K. Patel sir, and it is given in the codal provisions. Now special investigation is required for the seismic design of the bridges. For bridges which individual span more than 150 meter or pier height is more than 30 meter in zone 4 and zone 5, cable supported bridges such as extra dose bridge, cable stayed and suspension bridges, arch bridges having more than 50 meter span. In such all the cases, the special type of investigation like site specific response spectrum of the bridge, including geometrical nonlinearity, P delta effect and soil structure interaction is needed. Dynamic analysis may be done to ascertain the energy dissipation characteristic of ductile members. Second is the continuous bridge with length between expansion joint is larger than 600 meter in all seismic zone. Geological discontinuity or marked topographical features are present. Then again we have to go for a special studies and the investigation. Bridge site close to fault within 10 kilometer region which may be active in all seismic zone. In that cases, the information about the active fault should be sought by the bridge authorities for projects situated within 100 km of known epicenters as a part of preliminary investigation at the project preparation. With the help of this specialized literature as well as geological and seismological expert, we have to, with experience, enough experience will be required to calculate fault movement. Now, structural ductility and energy dissipation. Seismic design of bridge is generally achieved by providing adequate strength and ductility of structure. The energy dissipation takes place due to inelastic behavior of pier. The location of plastic hinge should be predetermined and the required flexural strength of the plastic hinge shall be obtained by using capacity-based design approach. This is the design approach. Now, PSC or RCC members substructure shall be designed as under reinforced and adequate detail to avoid premature failure due to shear and bond. Plastic hinge regions shall be provided with closed space transverse stirrups to confine the compressed concrete within the core region and to prevent buckling of longitudinal reinforcement. In steel structure, the compression zones require detailing to avoid premature buckling, and joint require proper detailing to ensure overall ductile behavior of the structure. Now, elastic seismic acceleration method. For most of the structure of low to medium height, small span and small length of bridges, elastic seismic acceleration method, seismic coefficient method is adequate. In this method, structure is analyzed for fundamental mode of 5%, that is single. Here we get the FH, that is horizontal force, is AH is the factor, seismic horizontal seismic load factor multiplied by dead load plus appropriate live load, where FH is seismic force to be registered and AH is the design horizontal seismic force. Now we can get AH by Z by 2. Z is the zone factor, SA by G is the seismic design acceleration coefficient, and R is response reduction factor, I is the importance factor. Now minimum in SP 114 also it is given that if we are not getting any AH for a flexible structure, then also we have to consider a minimum AH value. For the zone 2 is 0.011, zone 3 is 0.017, for zone 4 it is 0.025, and for zone 5 it is 0.038. So we have to consider minimum this acceleration for any design of the structure. Now different methods are given. That is simply supporting ideal span up to 60 meter condition, pier height is up to 30 meter above. Then ESAM, these methods are given in the codal provision. Now ESAM, that is the elastic seismic acceleration method, elastic response spectrum method, and ERSM is elastic response spectrum plus time history method, and elastic response spectrum and time history method with site specific study, that is for the cable stayed bridge and the extra dose bridges, etc. We require this type of studies. Now design provisions for the superstructure. For the ductility specifically, when the superstructures with simply supported span on bearing are vulnerable to damage because of they are prone to being unseated or toppled from the supporting substructure due to either shaking or differential support movement associated with the ground motion. In such cases, the provisions such as large seat width, that is the large cap, we can provide a large pedestal or this pier cap, etc. Using unseating prevention devices like seismic restrainer blocks, etc. we can provide. Then when there is this girder moves, this seismic restrainer holds it in the position. Holding down devices or interlinking of span by linkage should be made to prevent a span dislodgement of their supports. The superstructure should remain elastic even when the plastic hinge location in columns and on piers reaches their plastic moment capacity, and in order to ensure the elastic behavior of superstructure, capacity design principles shall be adopted. Now for the substructure. Plastic hinge should develop in columns rather than in capping beam of structure under seismic condition. Because if in the capping beam there will be the hinge formation, then it is probable failure of the superstructure will be there. So it is advisable to provide this plastic hinge should be developed in column only. The location of potential hinges in piers should be pre-selected so to ensure their accessibility for inspection and repair. The shear failure in column should be avoided by ductile design and detailing practice. Design provision for substructure. Piers shall be capable of resisting shear corresponding to the overstrength plastic moment developed in plastic hinge region. This shall be ensured by ductile design and detailing practice. Number of piers and abutments that will be resist seismic force in longitudinal and transverse direction should be pre-selected. Now design provisions for foundation. Force demand on foundation should be based on capacity design principle, that is plastic capacity of base, that is column or piers, multiplied with an appropriate overstrength factor. Foundation element should be designed to remain essentially elastic. Pile foundation may experience limited inelastic deformation. In such cases, this should be designed and detailed for ductile behavior, because pile is little bit flexible structure, and in the top of surface or up to fixity layer there is a movement in the pile, so it requires the ductile detailing. In case of well and pile foundation, the foundation should be taken deeper into soil layers where liquefaction is not likely to occur because of the reduction in the load carrying capacity. We have to go deeper if there is a potential of seismic liquefaction was there. Now, capacity design principle. The capacity to resist and dissipate energy are related to the exploitation of non-linear response in a structure designed to ensure ductile behavior. The location of plastic hinges regions are pre-selected to enable development of suitable plastic mechanism. The plastic hinge region are then designed and detailed for adequate ductility. All other regions are provided with additional strength called the capacity design effect, so that they may remain elastic when the selected plastic hinge is developed in the overstrained condition. Capacity design principle. To provide adequate margin of strength below ductile and non-ductile failure modes, capacity design is achieved by providing overstrength against seismic load in location adjacent to the plastic hinges, where which are to essentially remain elastic. The shear resistance of plastic hinges as well as both shear and flexure resistance of the other region shall thus be designed to resist capacity design effects. This principle provides the basis for ductile detailing of the reinforcement in bridge. Now we can see the potential hinge condition location in the column or a pile. Like in this case, we have a cantilever column pier. So in that case, we have this potential in both the direction, because the stiffness is almost same, or this may be rectangular, circular column or a rectangular square column, in which though in both direction there is a probability of plastic hinge formation. So we have to provide ductile reinforcement in this H condition, this shown in the H shown in the diagram. Same way for the pile top, that is the pile cap bottom, as well as the at the time position of fixity level, we have to provide a ductile reinforcement over there in both direction, transverse as well as the longitudinal direction. Here we can see the portal frame. In case of portal, when the force is earthquake force is across the traffic direction, there is a in this case, the moment and potential for hinge formation is there at the column cap bottom as well as the pile cap top. In that cases, we have to provide a ductile reinforcement over there. But in case of this longitudinal direction, there is no chances of this potential plastic hinge formation, because of this behave as a cantilever. But as a whole, we have to provide a reinforcement, ductile reinforcement in both conditions. Now, in case of wall type pier, where the one direction has a stiffness, more stiffness in that. In that cases, it is not possible to form a hinge in the transverse direction, but in the longitudinal there is a possibility of formation of hinge. So we have to provide the reinforcement, ductile reinforcement on basis of the forces in the longitudinal direction. But in case of pile, we have to provide this ductile reinforcement in that top region and the region where the fixity of pile is there. Now, length of plastic hinge, that we have to consider NK. NK is equal to NED. NED is here we have this design seismic force and designed axial force. AC is the area of concrete, and FCK is the characteristic of concrete. Now, when its ratio is this ratio is 0.08, less than 0.08 or equal to 0.08, then confinement is not required. But when it ratios come to higher, then we have to this motor more than 0.08 and less than 0.3. Then we have to provide this confinement or a confined plastic zone. We have to decide this length of plastic LH is equal to maximum of B. B is the width in which direction we are calculating the stiffness, and L is 0.8 of bending moment. 80% where the bending moment maximum to comes to 80% bending moment. It is a length L, so we have to provide maximum of from both B or L where 80% of bending moment is there. When NK is greater than 0.3 and but less than 0.6, then this force this length is multiplied by the 1.5 times. So we can find the length of plastic hinge zone in the structure. Or an additional length of LH, reinforcement provided shall not be less than the 50% of the above in the remaining portion. Right? We have to provide the 50% of reinforcement in the 50% of this plastic hinge zone reinforcement. These are the typical example of confinement details. Here we can see the distance ST1, ST2 at the center to center distance is given in the this different diagrams. So we have to provide this link not more than 200 mm spacing or B minimum by 3. Again, we have to check to prevent the buckling prevention. The confinement of steel may be provided through the set of hoops and the single leg cross ties. The hoops shall be engaged in longitudinal bars only, while the single leg ties shall engage both the longitudinal bars as well as the vertical bars, transverse bars, in the manner to show the 135-degree bent hook. Such ties need not to be complied with cover requirement as engagement of the location. At this point, the cover may be reduced because of this link is outside the confinement reinforcement. Here we can see the how the close lapping of the circular hoops are done. Now, ductile detail requirement quantity of confining reinforcement, that we have to find out on the ratio basis. That is omega W is equal to rho W FID upon FCD. Now, where rho W is the volumetric ratio of transverse reinforcement, these are defined as the ASW upon SL in B, where ASW is the area of stirrups and tie in one direction reinforcement. SL is the spacing of hoops or ties in the longitudinal direction, and B is the dimension of concrete core perpendicular to the direction of confinement under consideration, that is measured from outside of the perimeter of hoop. Now the volumetric ratio is different for both, for rectangular section and for the circular section. Here what we are finding omega dW, that is we either required is omega W required or 0.12% of the volume. So omega W required, again we have to find by 0.37 AC upon ACC. AC is the area of concrete and ACC is the area of confined core, right, of concrete area. Multiplied by NK, what we have find out previously, plus 0.13 FID upon FCD into rho L minus 0.01. So we can get the required reinforcement, and we have to check whether this maximum of this required reinforcement or 0.12% that we have to provide for the confinement. Right now, for the circular column, the value will be rho W will be 4 ASP upon DSP into SL, where DSP is the diameter of spiral or hoop bar, and the ASP is the spiral area of the spiral or hoop bar, right? And SL is the spacing of the these bars, spacing of these confinement bars. And omega WD is maximum 1.4 times the required or 0.18. Here it requires more steel with compared to this rectangular section. The minimum longitudinal reinforcement and concrete grade shall not be less than 1% and 30 MPa respectively. Now, minimum amount of transverse ties, that is also to be calculated, where here it is given AL upon SL is the A1, AL is the area of one tie leg in mm square, SL is the spacing of legs along the axis of the members, sigma is the sum of the areas of longitudinal bars in outer layer restrained by the tie at a time of one end. That we have to calculate. FIT is the yield strength of tie, FI is the yield strength of longitudinal reinforcement. Here it is given how we have to consider calculate the area of stress AS shall be determined by the following situation. AS for determining AL is the area of this link is given by 0.5 of ASL1 plus AS2 plus 0.5 AS1. That is the half of the both the longitudinal bar. Same way for the corner also, we have to consider 0.5 into AS1 plus AS2, and for inclination we have to divide by the sine degree of the inclination. So it gives little bit higher area of the steel. Now minimum amount of transverse tie shall be along the circular section of boundary restraining of longitudinal bars should be achieved through the circular ties determined by the A1 upon SL 1 upon 12.8 rho 1 d square into FISYT. Right, A1 is the area of one circular tie in mm square. SL is the spacing of circular tie along the axis of the member in meter. Rho 1 is the reinforcement ratio of longitudinal steel. D is the diameter of circular section in mm. FIT is the yield strength of tie, and FI is the yield strength of longitudinal reinforcement. These are the calculations for the ductility. Now for the foundation, it is desirable to inelastic response in strong ground shaking occurs above the foundation, as repairs to foundation can be extremely difficult and expensive, as it is very, as we know that for repairing of foundation it is very difficult, and particularly in the bridge structure we have a deep foundation. So in that cases, we have to avoid any hinge formation in the foundation. So also the code has provision that whatever be forces coming in the pier base is to be multiplied by 1.35. That is 35% more forces is taken for the design of foundation. Now code does not allow foundation to enter within a plastic range under design seismic action except from pile foundation in unavoidable circumstances. So the designing of foundation for 35% additional base shear in on account of seismic action as specified in IRC 6 2017. So the weakest link within the pier or at the pier of base. That is when we are considering designing the foundation, we have to increase the 35% force, seismic force for the design of this foundation. To ensure adequate ductility at the plastic hinge location by proper detailing and confinement for pile foundation as hinge formation is allowed if unavoidable. Normally we are not allowing, but for a large scour where there is a large scour or we have to provide a flexible condition for the pile, so unsupported length is increased. In that cases we have to allow some portion of this plastic information. Now, seismic isolation. Seismic isolation is one of the most popular means of protecting structure against earthquake forces. It's a mechanism established by structural element which should be substantially decouple a superstructure from its substructure, which in turn reduce the seismic response of the structure considerably. It's isolate the structure from the ground shaking by suitable device which will absorb the shaking by its own deformation and damps the vibration for the structure. Now, as SK Patel sir has explained that this roller rocker bearing, a rocker type bearing is not now, it's a rigid type of bearing. So in that cases, the forces is transferred directly to the substructure. So demand is more for the seismic as in the bridge structure, we have large mass for the superstructure. For last one, we have the number of this girder is more and the mass is more. So the large amount of earthquake force is generated due to the inertia of this mass. In that cases, we have to reduce this seismic force to be transferred to the substructure by means of providing this type of seismic isolation or a flexible bearing like this elastomer bearing or cord PTFE bearing. We can reduce the force transmitted to the substructure. Seismic wave propagate from the ground to superstructure through the substructure. Large initial mass of superstructure cause a large seismic force in the entire structure. Quantity of seismic motion actually experienced by the structure largely depends upon the seismic response of the structure. The response can be reduced by providing isolation devices between substructure and superstructure in the case of bearing supported bridges. Now, seismic isolation devices are like hydraulic viscose dampers, elastomeric bearing damper, low damping elastomer, high damping elastomer bearing damper, lead rubber bearing damper, and friction damper. These are the different type of dampers. In some cases where large forces are there from the superstructure, this is the provided over there. Provision of isolation device is optional and it may be decided by the engineer on the case to case basis. That depends upon the design and the foundation, which type of founding strata is available, and this all depends upon the design conditions. Various types of isolation devices have different mechanism of seismic force reduction. Seismic isolation devices covered in this chapter are permitted to be used for comparatively rigid structure where fundamental time period T of the structure without incorporation of seismic isolation device is less or equal to 0.1 second. In case of type 3 type soil, seismic isolation device may be avoided. These are the some sketches for the seismic isolation. You can see the internal rubber steel plate. It is same as these our elastomer bearing type of this rubber is elastomer bearing is there, and there is some special system is made for the like lead rod is placed in the center of this bearing. So here multi-layered natural rubber is there. This is a one type of seismic isolation device. This is provided over there. Thank you. So for this type of ductile detailing, as I explained, we have to avoid the failure in case of seismic. The ductile detailing is always to be very critical, and we have to address in such a manner that we can avoid the failure of the bridges. Thank you. Thank you. Any questions, sir?
You can ask the questions. Please unmute yourself, and if you have any question, please ask. Hello.
Hello.
Sir, 1 minute. If anybody says question, please ask. Er.J. Patel sir is with us, so please ask the question if you have. Please raise your hand if you want to ask questions. And I request Professor Bansal to unmute participants, please.
Already unmuted, sir. Already allowed to unmute here, sir.
Okay. Right. Yes, please. Sir, I want to ask one question. Okay, before that, I think Praveen, Mr. Praveen want to ask question. Yeah. Please.
Hello.
Yes, please.
Sir, I have one query, sir. If the bridge is fall in the line of zone 2, zone 3, then for how we tackle this type of condition? If the bridge passing through the line of zone 2, zone 3, two boundaries.
In that cases, you have to consider the zone 3 because it's considered as a near field region, not only for the fault, but also for in case of this zone line, because zone 2 and 3, if we are within zone 3 line, normally what happens, we are considering potential of the seismic over there. But in when you are near to zone 2 and 3, then you have to go for zone 3.
Sir, for the entire span or up to the certain length, or for the entire span?
Entire bridge.
Entire.
Your bridge length is maybe our in Gujarat.
400.
Bridge length is 1 kilometer, 1.2 kilometer.
Sir.
So it comes in the entire the bridge is coming in the zone 3, and always we have to go for little bit conservative side.
Okay, sir. Thank you, sir.
Yes, Mr. Anuj Kaushik Kumar. Yes.
Sir.
Yeah. Yes,
can you hear me, sir?
Yes, yeah. You're audible.
Yeah. Okay. So my question is, which are the different parameters we have to consider while designing of any bridges for the particular type of the bearing point of view? Like if we want to construct the normal supported bridge, then this type of the to consider while designing of the bearings. And second one is, whenever if the curvature is there, because if you remember in Surat, there are 1 or 2 bridges were collapsed in the form of curvature portions. When the investigation team says it is because of the improper design of the bearing, right? So which are the different parameters we have to consider, keep in mind while designing of the bearing for such type of the any bridges, like double state bridge, curvature bridges, and say iconic bridge type of any structures?
Yeah, I got a question. Now, in case of Surat bridges, let me come to that bridges. For any structure, we have a basic 3 fundamental equilibrium condition. Sigma V is 0, sigma H is 0, sigma M is 0. Right? Now, in case of this Surat bridge, if you are going with the central line to the curvature line, the eccentricity of load is there. So what happens? There will be a pressure. One bearing has got the uplift pressure. One bearing has got the download, one get the upload, because whatever be moments, if we are simply supported beam, we have to support and we apply moment at the center. What happens? There will be one downward reaction, one upward reaction. Right?
Okay.
Got it? You hearing me?
Which are the different parameters to consider? like any it is not available, mostly it is not available in India, but in foreign countries some special shapes bridges are there.
Yeah,
So while
so in that
bearing
yeah,
of the bridge, what we have to consider?
hold down devices. Nowadays in India also there is some bearings are there in which we have like a piston key type of condition over there. In that cases we can consider as a hold down devices. We can also provide McAlloy's bar in some cable state bridges where abutment there is uplift force is there. In that cases also we are providing the McAlloy's bar to hold down the structure. So bearing normally what happens in for the simply supported span and the large span, we have some restriction because of the elastomer bearing is used for the vertical load transfer and lateral movement. But when our span is large, there is a very large deformation because of the seismic force. So in that case, this elastomer bearing cannot resist. In that case, we have to go for the pot PTFE bearing, in which also we are providing one fixed bearing, and on the other end, we have to provide a longitudinal guide to allow the horizontal movement for the temperature, shrinkage, etc. We have to provide a horizontal movement. Also, at that same time, we have to restrict the force transverse movement because of the seismic force. So in that cases, we have to provide in some cases we have very large forces. In that cases, we are providing with the pin bearing. The function of pin bearing is to resist only lateral load, not a vertical load, right? In that cases, we are providing this bearing with pin bearing. But now looking to all these conditions, seismic restrainer is in our government of Gujarat as per codal provision, seismic restrainer is not mandatory in zone 3. So we are insisting and we are providing a seismic restrainer. It will definitely help to this superstructure dislocation in case of the heavy seismic force.
Okay. And sir, one more another question that whenever we are up till now, very few buildings in Gujarat, if we are talking about Gujarat, then very few buildings they are providing the bearings at the in the form of base isolations point of view. But why it is not more popular in Gujarat? Is there any reason it is most costly than the other methods, or because if we are providing the bearings in the form of say like a base isolator, it will be good in earthquake point of view.
Now in case of Gujarat, nowadays we are coming with a building with more than 20-30 floors. In that cases, the basic seismic isolation is needed. At now recent 2 or 3 years, now high-rise building with 40 story, 50 story is becoming popular in Gujarat. So now whenever it is required, they will definitely go for the base isolation. Because for the 10 story, 12 story, and again one more thing is for the building structure, number of columns are there, redundancy is more. Right? So base isolation is required only for the zone 5 where there is a large forces is there. In that cases, this will be popular, but in the Bhuj or etc., there is no high-rise building. No, I mean not more than 6-7 story building are there. Whenever we high-rise building, then base shear is more. In that case, the seismic isolation device is required. So now it will be popular because if you are going in Maharashtra, there is a 100-story building over there. So in that case, it is required.
But sir, nowadays some of the buildings in Surat also they are individual floor level they are providing the swimming pool to the flat owners. So in that case, whenever the earthquake striking to the structure, it will behave the drastically behavior change in the because that slow movement of water.
Dynamic force over there. It means increase the seismic force. In that case, it is required. But this swimming pool building is, I think, it is 11-story building, not more than that.
Yes.
But now they have one committee for the high-rise buildings. The Gujarat government has formed the committee. In that, S.K. Patel sir is also one of the members. So in that case, whenever we required now in the Gujarat this scenario starts, so they will go for the base isolation over there.
Okay, sir. Thank you, sir.
Yeah.
Okay. Hello.
Hello. Sir.
Hi. One participant asked the question: cost of bearing with respect to cost of bridge.
Yes.
Can you mention?
The cost of bearing is not that much in case of bridge structure, because the bearing cost is very less with compared to bridge structure. Like if you are providing elastomer bearing, the cost of bearing 1 cubic centimeter cost is around 1.25 rupees. And total bearing cost it comes to is like for span it comes to, and if we are going for this, suppose we are considering 30-meter bridge, the load is 200 ton, 600 means 60,000, 50-60,000, not more than that for one span.
Actually, the cost of isolators as far as buildings are concerned, it is too high. You have cost of bearing is basically not that great.
Because normally what happens is up to 30-meter, 40-meter span, the bearing cost is not much more than for this structure. And we have this seismic restrainer block. We are providing seismic restrainer block also over there. When we are providing this elastomer bearing without seismic restrainer, then we have to consider seismic response reduction factor R is 1. We have to design for 100% force. If elastomer bearing is primarily used to transfer this lateral load. In that case, R is taken as 1. In that case, structure is very high, means heavy. But in that case, we have to, our structure is in elastic zone only. So our overstrength factor, again, we have not to consider. That is, we have not to consider 35% more forces for the foundation. But bearing cost is not more in these bridges. And normally what happens, failure is because of the poor maintenance only. And pedestal, normally what happens, pedestals are crushed because of the poor quality of concrete. Pedestals are casted after casting of cap. So there is an issue regarding this quality also there. If it is casted with the this PR cap, then we get the good quality of concrete.
Right.
In sir, one Rang Setu bridge is as sir has shown that Chandod Poicha road. Right, on the 8th of this last month, I visited. One pedestal was crushed, so the one side span is settled. There's upstream and downstream. Then upstream side is settled by 100 mm, and then downstream is at the position. So we have restricted the vehicular movement. Heavy vehicles are restricted over there, and now we are going for the repairing of that.
Right. Sir, one question from my side. Like as far as Gujarat is concerned, now we have entered in 2020, and lots of bridges require, I think, rehabilitation. Rehabilitation of bridges are required.
Yes.
Because they are crossing certain age, and I think it started like Rang Setu, what you explained.
Yes.
So many bridges are facing problems. So then, what is the scope actually as a retrofitting of these bridges are concerned?
So the retrofitting scope is, I think it is very good scope, means very potential, very much potential, because of the number of bridges are 50, more than 50 years old bridges require the strengthening as well as the structural seismic retrofitment. So the scope is very good, I think. And one more thing is any bridge collapse or we have to repair, then it is very difficult, because when this bridge was constructed years back, the traffic was very less. Now what happens, sir, is like we are facing problem as the SCI, with the development of SCI is in the past 10 years or 15 years, not more than that. But graph is unpredictable. We can predict the traffic growth on the our normal formula, right? When the number of multiplied, but number now factor is different, GDP is different, the development program is different. So retrofitting has a very good scope because constructing new bridge by diverting traffic is very difficult.
Right. And sir, one more question regarding the behavior. Like when we are talking about the IS 1893 provisions and IRC, then sometimes we find a contradiction because we believe in the ductility where we allow the large inelastic deformation, and sometimes the bridge engineer feels that the deformation should not be allowed, larger deformation should not be allowed. So what is your opinion regarding this
So far as this infrastructure, bridge structure is concerned, the large deformation shall not be allowed, sir.
Yeah.
Because it gives some also difficulties in like joint also is disturbed by that, or bearing may be disturbed. So large deformation is avoided in this bridge type of structure.
Right.
Hello, sir. Hello.
Yes.
Yes.
I am from Western Maharashtra. We have Krishna River. Krishna Rivers, there are flood problem in 2005 and 2019 also, and most of bridges submerged. So previously, as per old code, they have designed and they are not consider water pressure and earthquake loads also. So what are your suggestion for these type of bridges?
That all depends upon your foundation condition. If it is foundation in the rock, it is definitely we can retrofit, we can raise the structure, it is very easy. But if foundation is pile foundation or well foundation, then it is difficult to retrofit or change our height, etc. If you have bridge at the time of designing, you have considered like 100 meter HFL. For example, you consider 100 meter HFL and road level is 105 meter, right? Including superstructure depth, freeboard, etc. All the thing. Now your flood is at the 1.105 meter, 1.6 meter. Then your bridge is submerged. Now we have to raise the bridge to certain level. If foundation is on the rock, we can do easily. But if it is in the pile or well pile, again it is difficult for the retrofitting of that bridges. So we have to consider other way how to retrofit. Because only substructure is visible, foundation retrofitting is very difficult. So in this also for ductile detailing also and this seismic design philosophy, foundation information is not allowed in the foundation.
Okay, sir. Thank you,
but
sir.
It is in a rock, open foundation in rock, it is very comparatively easy to retrofit and raise the.
Okay, sir. Thank you.
Yes. Any more questions? So I don't think any more questions the participants having, and so we end the session here, sir. Er.J. Patel, sir, thank you very much.
Thank you very much
for spending your valuable time and sharing your expertise.
If anyone has any question, you can share my email ID and my number, sir.
Sure, sir. We'll share your number and email ID. And if anyone is interested, I think Er.J. Patel sir has done extensive work on the bridges, and I think he will be very much helpful to you in any circumstances. Sir, thank you very much once again, and for spending your valuable time here. And I hope in future also you will give the same support as usual. Thank you once again, sir.
Anytime, sir.
Yeah, thank you, sir.
Thank you.
Shruti.